it seems like you've conducted a number of different experiments, the experiments with DrawnApart on the GPUs, as well as the other experiments with the machine learning on the various data, and then the experiments with FP stalkers. So it's quite a lot of work. Interesting experimental setup on the DrawnApart work, and I can imagine there's a lot of different aspects of the experimental work that would be of interest to people. So let me go ahead and open it up and see if anyone has any particular questions or comments they'd like to make. And yes, please go to the microphone so that others in Zoom land can hear.
Hi, Jeff Boot with Netflix. I'm curious, if you're trying to track a user from an ad perspective, right, then you're trying to look for how similar they are, and so you can find the accounts. But if you're looking at it more from a blue team perspective, say, I don't know, protecting against account sharing, then you actually are just trying to say, are they still on the same device or not, probabilistically. And so I'm curious if that you can do that more efficiently.
When you got the DrawnApart trace, you can measure the distance between any other DrawnApart trace that you want using the embedding CNN. So you can take any two traces that you want. So if you have a specific account, you can record the embeddings of the login from a specific device, and then record the embeddings again, and see that if the distance between them are big, so they probably came from different devices.
Okay.
I hope that it answered your question. If not, please send me an email and discuss it offline.
Yeah, that sounds good. Thank you.
Hi, I'm Isaiah from George Washington University. I had, I think, a similar question. So the input to the convolutional neural network, that's the images produced by the profiler, right?
Yes.
So two GPUs, even if like everything else is the same, may not have the exact same image or fingerprint. So if the similarity between two images is not the same, and presumably the similarity between the embeddings is the same, like the embeddings are close together in embedding space, even though the images themselves are far apart.
Yes, it's actually like face recognition. For that example, you can have entirely different pixels inside an image, and it will still generate the same embedding, or like embeddings that are close to each other. So this is the idea here. The network was trained using triplet loss, and the idea of triplet loss is making all the embeddings of the same device closer to each other, while keeping the embeddings of different devices and further away from these embeddings of this device.
Okay. So then how do you prevent overfitting, where like how does it treat completely new fingerprints it's never seen? Like, what was your validation process to prevent overfitting? Or it seems like you almost want to encourage a little bit of overfitting if the inputs can be so different from each other.
I'll share my screen for a moment. What we did is that we used this dataset split in order to verify that we are not overfitting. In order to evaluate that we are not overfitting on the labels that we trained on, we use the 1NP rest dataset. So it has different labels than what we trained our neural network on, and the results are still pretty good. So it means that it works on other labels as well. As in any deep learning algorithm, overfit occurs, and it's something that you should account for. Probably our network is better on devices that it was trained on.
So one question I have is the one data set that you mentioned with the, 370,000 samples. Did you collect that yourselves, or was that already available from another source?
So actually, the dataset with that much data, we collected it from the Amazonic extension. So this is a large crowdsourced experiment that we had for a little while. So we have real users from different parts of the world on the extension, and we collect every few hours their fingerprint, and along with the fingerprint, we collect the trace with all the necessary attributes that DrawnApart needs. So this is how we collected it.
Okay, great. And is that data set, do you make that available? Are you sharing that with the community so others can use it?
So in this data set, we have attributes that can be used to identify the person. So we couldn't make that available to the world because of privacy issues. However, I think that Tomer and I made available an anonymized or randomized dataset, but the original dataset that we put in the repository is not the dataset that we gathered. When you install the Amazonic extension, they give their consent in order for us not to share the data. So that's why you couldn't share the data that you connected.
Yeah, that makes sense. But if there's a way to figure out how to appropriately anonymize it so that it's still useful for others, it would be nice to make that available to the community. Are there other artifacts coming from your work, from your experiments that you're able to make available? Is the DrawnApart software available for others to use?
So we have a GitHub repository that we put in this slide. I'm going to share my screen so people are able to see it. So in this GitHub repository, we put all the code that we wrote. So we put the adapted version of Epistalker. We put the results of the adapted version of Epistalker. We put the DrawnApart on-screen, off-screen GPU code. So everything is available in there except the dataset because of obvious privacy reasons.
Perfect. That's great. I'm glad you're making that available.
So I'm curious, is there an experiment that you would have liked to have run, but you couldn't because you didn't have access to, data or some infrastructure component that would have helped?
So I don't think that we have experiments that we wouldn't run because we didn't have the infrastructure to do so. The way that we picked the stall function is by looking on the machines that we had in our lab, and we didn't have a lot of machines in our lab. Like we have only a limited amount of identical devices. If we had, 100 sets of identical devices, we could have picked a better stall function and we could do experiments on that. But we really picked what looked good for us on the small sets of devices, on small different sets of devices that we have available in our lab.
Okay, that's interesting. That's helpful. Real quick before we wrap up here, what are sort of your next steps? What are your plans for the future? Do you anticipate doing a post-laser workshop paper that talks about what you presented here today? And then what is some other future work that you might be doing? For example, one thing I noticed is, some of the accuracies that you mentioned, they seemed pretty good, but obviously they're still fairly low. And so do you anticipate any optimizations in the future?
And yes, we can do our optimizations on the runtime. For example, instead of memorizing all the traces on all the embeddings, you can maybe memorize only the mean value of the embeddings, and it may result in a better accuracy. And there are also newer inactive developed GPU APIs on the web GPU, for example. And we plan to develop an attack dedicated for web GPU to use all the new web GPU features that WebGL didn't provide.
Okay, great.